Okay, so this is the first time that I do this. Welcome to this first podcast. As our first guest, we have the pleasure of having Dr. Tomaž Prosen. Dr. Tomaž Prosen is a Slovenian theoretical physicist working in the field of quantum physics. He has won several awards, including the Physics Prize Dresden, the Bessel Award from the Alexander von Humboldt Foundation. He has several papers and many renowned publications and many renowned journals. So it's a great pleasure to have it, Tomaž Prosen as our first guest. Thank you for accepting the invitation.
Thank you.
Okay, so if it's okay for you, we could start with the basics. So basically, how do you remember like the first time you were interested in physics, or that you consider physics as a career option, or like in a more serious way to make it a career?
Well, I mean, I got interested in physics very early in my childhood. I remember probably I was 10, 11 years old when I learned what physics is. I remember there was a book, this was the times where nuclear energy was still very, 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 very not only important but also popular in society. So I remember finding a book about the atom by Walt Disney in the school library in primary school when I was like 10 years old. It was almost like a cartoon book, but with some text and some, yeah. So, I mean, I was so fascinated. I said, wow, this is something I want to learn about. And then I think when we had first kind of course in physics in fifth grade in primary school, I think I came to home after the first day of physics. I told to my mother, look, I mean, I want to be a physicist. So, I mean, I was very determined. So I didn't hesitate at any point. I mean, after this time, I was determined that I want to be a physicist. Of course, I didn't know that this could be my career. I mean, this I kind of, I mean, you don't know, as a child, you don't imagine how this works, right? But, I mean, to me, it was really like a straight path, yeah.
Okay. And also, I imagine that you were particularly good at mathematics, because I think sometimes it can happen that maybe you see a documentary or something and you can get interested in physics in a more superficial way, let's say it. But I mean, the truth is, like, when you do physics, it's mostly, I mean, a lot of it is mathematics, so it's not enough to maybe appreciate in a more superficial way, but it's also, I think, important to be good in logical stuff or mathematics and things like that. So I guess that was also one of your interests?
Sure. I was always better in physics than in mathematics, at least compared to my peers. I mean, like in school. Like, okay. I mean, I participated in competitions in physics and mathematics, but in physics I could, be much. My results were more visible, let's say. I could not, at that time this was like times of former Yugoslavia, where it was a big country, where it was, lots of, very competitive. So it was very hard to be selected for Olympiad or even to one national competition. So in physics, I was able to, let's say, to be on the level of national competition or getting prizes in the national competition, not in mathematics. So I was always interested also in mathematics, but I was kind of, even now, I'm not so sure whether I should not pursue career in mathematics, but I mean, it was always kind of swinging between theoretical physics and applied mathematics in a sense. But
yeah, I understand it's not the same, because you mentioned Yugoslavia, because when you were a kid, it was still Yugoslavia. I know it's not the same, but I know that in the Soviet Union, for example, they have like specialized programs for students that were particularly good at mathematics. They have like a specialist class to like make them advance further and not like slow them down. I don't know, in Yugoslavia there was something similar, or it was like a general system?
Not really, but we had special schools for let's say, at a time, actually it was just at a time of some sort of reform of high school education. When I was attending high schools, so they had specialized high schools for mathematics and sciences.
So I guess that helped you a bit also?
That helped me a bit, yes.
Okay.
I had like 20% more mathematics than in the regular gymnasium.
Okay.
That helps, but I was happy that I got this option, because then they cancelled these specialized schools a couple of years after I finished. So they thought that was too specialized. I liked it. I really liked it.
Okay, that's cool. Okay, and so it seems like to some degree it was always your main interest within physics was quantum physics or the atom. Or it seems like from early on that was your attention the most from physics?
Yes. That's why also as a student I decided to, because in Ljubljana I studied at Ljubljana University, and we had to decide for a kind of direction after second year of studies. And I decided for particle physics and field theory, even though what I'm doing now is more like condensed matter related, or let's say more abstract theoretical physics. So I started more with interest in particle physics, but then I realized, first of all, in Ljubljana, particle physics is not so well developed, I would say, at least not theoretical particle physics. And I didn't want to, for some reason, I didn't want to go to study postgraduate abroad, so I decided to do chaos theory. I found a very good advisor in chaos theory, in, let's say, Hamiltonian and quantum chaos, which was also a very hot topic at the time when I was doing PhD. So this was my first kind of choice. And then I kind of drifted towards more quantum many-body physics during my career.
Okay, I see. So you mentioned chaos. I was actually trying to start a way to talk about your research. So I was reading some of your papers, or at least skimming through them. And two of the concepts that I think that appear the most, one is integrability, and the other one is chaos. And I think these two concepts, you have to do research in many topics within quantum science, but I think these two topics are the ones that appear both in your early work, but also in your present work. So maybe if you can start defining, I don't know which one you would like to start, either chaos or integrability. I know they're not the same, but just I feel that there were two topics that appear a lot in your work. So maybe if you can try to define them in the way that you understand them, or that you think is good.
Yeah, you see, naively, you might think that you may say that chaos and integrability are kind of the two opposite sides of the coin, right?
Mm-hmm.
They're kind of exclusive. The system can be either chaotic or integrable, but not both. So, and the mathematical methods to study integrable systems and chaos appear to be very different, at least, in most aspects. So, but I was interested in both, and in particular I was interested in exact solutions. In what can you say exactly about dynamics? So, if you want a common denominator between the two, is called dynamics. So I was always interested in time-dependent phenomena, non-equilibrium phenomena, and these can be studied within integrable systems or chaotic systems, and they can be, dynamics can be characterized in the two classes, but it's very different. As we know, in chaotic systems, dynamics is unstable. At least in classical chaotic systems, in quantum, in integrable systems, dynamics is predictable. You can basically confine it with knowing all the conserved quantities of the model. So, yeah, but you're right. My career was always kind of swinging between integrability and chaos.
Okay.
Even in my early papers has titles like Between Integrability and Chaos. So, in classical Hamiltonian dynamics, of course, this boundary between integrability and chaos is very interesting. It's fractal boundary, basically. It's, there is this KAM theorem, Kolmogorov-Arnold-Moser theorem, which tells what happens to integrable system once you try to break integrability, when you add integrability breaking perturbation. And this has been clarified in classical Hamiltonian chaos decades ago, in 60s of last century. But it's still a very exciting open question. How does quantum many-body systems behave when you break integrability? When you're going from integrable system towards chaotic system? Where is the transition? What is the nature of this transition? Is there a transition? Or is it just a smooth crossover? So these are questions which kind of puzzled me already 25 years ago when I started to become interested in many-body. And still now, they're still kind of state-of-the-art questions of the community. So I think it's a very, very, very fruitful question. But as I say again, the common denominator of all these questions is dynamics.
Okay, I see. And also, I never had work in chaos, but I'm curious about it, and you can correct me if I say something wrong, of course. I think in classical dynamics and classical physics, let's say not quantum physics, it's more or less, it's quite clear. It seems like there's an established theory about chaos.
Yes.
The way I see it in an example is like you can have in a chaotic system, classic and non-quantum physics, is that if you change the initial conditions even by a little bit, you can have very different outcomes. Mm-hmm. And also, I guess the fact that you cannot predict, solve them for a very long time. So I guess that would be fair to say.
Yes.
How would you define quantum chaos, or in which ways will it be different than classical chaos?
Well, this is a very interesting question. It's still this question is still objective of research papers even today. I mean, there is no consensus in the community what exactly quantum chaos means. So there are at least two different takes on quantum chaos. Because first one can define quantum chaos as the phenomena in quantum physics which correspond to which happen in systems which have classical limit and whose classical limit is chaotic. This was a traditional definition of quantum chaos in the 80s and 90s, but it essentially applies to single particle problems, because for many body systems, well, you can also apply this definition, but it's sometimes hard to define what classical limit means. For example, take a spin chain. For spin 1/2, there is no classical limit. Okay. Or fermionic systems, some Fermi-Hubbard chain, there is no classical limit. So for those systems, it's hard to define the corresponding sensitivity to initial conditions that you mentioned, for example, as a definition of chaos. So in classical dynamical systems, as you say, mathematicians have defined precisely what is meant by chaos. I mean, there is Lyapunov exponents, there is Kolmogorov entropy, dynamical entropy. So people can classify dynamical systems into classes, and they have rigorous examples within each class, and these examples can be treated. In quantum many-body systems, there is so far, well, I mean, I think I should say probably our work was kind of in this way pioneering. I mean, trying to define classes of quantum many-body systems for which you can define precisely what you mean by chaos. For example, I mean, in recent years we came up with this concept of dual unitary systems, for which we can prove, at least to some extent, and we can prove some properties of these models, and we can prove that they are given by random matrix theory. So that's another, I would say, more abstract definition of chaos, which is that dynamical features of structured models with structured interactions, like local interactions, is equivalent to random matrix theory, to statistical properties of random matrices, which are completely unstructured, right? Okay. I mean, there is no locality, there is no notion of space in random matrices. Random matrix is just a collection of states coupled all to all, and you define a random matrix as a Hamiltonian, and then you study the spectrum, for example, or eigenstates, and you compare this to the spectrum or eigenstates of your dynamical system, which has defined for a given physical system, like a spin chain or some array of atoms and so on, with specific interactions. So I think this is I mean, to me, at the moment, the best definition of chaos. I mean, it's the correspondence of statistical features with random matrix theory.
Okay, I see.
So if the model has statistical features which correspond to random matrix theory, I would call it chaotic.
I see. To be honest, I have read, like in many papers, you see this concept, random matrix theory, but like, for me, honestly, it's a bit hard to grasp in the sense, why is it important, or how, or why a relation with random matrices, why does that give you information, or why is that?
It does give you no information, that's the point. Okay. It's universal. I mean, random matrix theory allows a universal description of some dynamical or spectral properties of your model.
Okay.
For example, I mean, usually people consider spectral statistics when they compare to random matrices. So you consider your Hamiltonian system, you diagonalize it, so you consider stationary states. You look at the energies, which excited energies, which correspond to stationary states, and then you look at the spectrum of excitation energies. And that spectrum, of course, is model dependent. I mean, different models have different spectra, but if you look at it as a statistical object, like a gas, then statistical properties of that spectrum can be described very well by random matrices, like two-point function. I mean, the density of this gas, of course, is model dependent. I mean, depends on whether you have 10 or 20 fermions, or what are the precise interactions. But the correlation features, not the density, but the pair correlation features of the spectrum can be completely universal and given by structuralist theory, which is random matrix theory.
Okay.
So zero information.
Okay, I see.
You see, I mean, it's without free parameter. That's the point. Okay. The spectral properties can be described by a theory without a free parameter.
Okay.
It's actually so fascinating about it. No, that's no fitting, no model dependent parameter. It's completely universal.
I see.
So chaos is universal. I mean, it's different than in integrable systems, which are which are very different. Each integral system is different from another.
Okay, and since you have worked for some time in these two areas, how would you evaluate our understanding of chaos or integrability from when you started your research till now? Like, how would you evaluate the progress? Like, how much do you think we have advanced in this, in the understanding of these two subjects, and how far are we? Not an ultimate answer, but like maybe because you say that a quantum case is not. Yes, there's maybe some definitions, but I mean it's still to some degree a debatable topic, I guess, the definition. So how do you evaluate their understanding of this subject in your career?
I mean, evolution of these concepts has been amazing. I mean, I could not imagine this type of research 25 years ago that we are doing now. But we had to introduce new concepts, and some of these concepts that we are discussing now did not exist decades ago. So, in the beginning of my career, in the early 90s, I mean, that sort of chaos research, the quantum chaos research, that has been basically declined. It's very, I mean, now has been reviving because of many body, but that single particle quantum chaos has basically been declining, and the main kind of questions they are shifted to mathematics. Okay. I mean, because as usual, you try to motivate mathematicians to prove theorems, right? At the end, you want to really have a full rigorous control, and quantum chaos has become more or less part of mathematics, or let's say rigorous mathematical physics. But in terms of physics, it kind of lost physicists lost interest in chaos until I would say. I would say these papers from high energy physics were probably first that raised attention to chaos, like Schenker, Maldacena, Kitaev, Stanford. These people have, they proposed again the idea was this out-of-time order correlation functions, and they referred again to these old papers by Larkin or Chinikov, which mapped out-of-time order correlation functions to Lyapunov exponents. I mean, that's very traditional. I would say this is very traditional. It's semi-classical chaos. It applies also to single particle problems. But in field theory, you require this large N regime. Okay. But it's still. I mean, I think it was very important that these papers kind of brought back the questions of chaos, and also they expanded the community of people who are interested in chaos. I mean, when chaos penetrated to high energy physics, there were like thousands of physicists doing black holes and quantum gravity suddenly became interested in chaos. And it's really, and now they are interested also in quantum circuits. Okay. So completely different phenomenology than OTOC. Okay, I see.
I find very interesting that because at first you say you decided to, instead of high energy physics, you went into chaos at the early of your career, but I think it's very interesting how there was a return to the question of chaos that it was raised by the high energy physics community. I guess that speaks to, that kind of tells you a bit how the science works in a way, in a field, there can be advanced scenario that comes from an area that you didn't expect it maybe, and like how this, at the end I think it's a collaborative process that happens not only between the groups but also between different areas.
Exactly, yeah. There is this cross-fertilization between fields, which is very important. Like in particular, I mean, not only high energy, but it's particular subfield of high energy which has been instrumental here. It's just the so-called ADS-CFT or holography. Right? And okay. These people who did holography, they were the people who then started to do quantum chaos. Okay. So they found this. These first models. I mean, these canonical models of chaos in high energy physics. They are the holographic models.
Okay, I see. Okay. Because you say that right now there are different tools to study chaos, and I mean one of the things that maybe makes you advance on research is that at the end you also need mathematical tools, or not. You need some framework to deal with some problem. And I think one of the tools that you use now that you are very interested is about dual unitary circuits. Mm-hmm. So I don't know if you can explain it, because I believe that this is some subject that interests you a lot, and I think that you're working currently this one maybe.
Precisely, yes. Thanks for this question. I mean, this is really something that, I mean, as you mentioned, I mean, and this connects to one of the first questions. I mean, I'm really interested in tools and methods in theoretical physics. So that's what maybe makes me more mathematical than a typical theoretical physicist. I really like to think of abstract tools. And these dual unitary systems that we introduced a few years ago, I mean, these are really a tool which allows you to study chaos rigorously. So it's a special class of models, if you want fine-tuned models, for which you can derive certain dynamical properties exactly without any approximation. For example, in these dual unitary circuits, you can compute spectral correlations, the so-called spectral form factor, which is just a Fourier transform of pair correlation function, or you can compute the dynamical correlation functions of local observables, so correlation between two observables into different points in space-time. So these are 1 plus 1 d-dimensional models. They don't have to be 1 plus 1, they could be d plus 1.
Well, with 1 plus 1, you mean like one spatial dimension?
One spatial,
and
one time direction, yes.
Perfect.
And they are discrete in both. So that's important. They're discrete in both, so they are kind of circuits. I mean, but we like to think of them as quantum circuits. If you like another language, you can also think of them as a quantum cellular automata. They can also be phrased as cellular automata, it's the same. So they are discrete in space and time. But the defining feature of these models is that you can change space and time. So you can think of these models to take an initial data, which is at equal time, right? So, this is the usual kind of problem. It's like a Dirichlet problem, right? You start with the initial data, and then you do dynamics. And then you ask what is the state after some time. Now, in these models, you can change the space and time, and you can ask whether knowing all the multi-time correlation function at a given point in space and all times, whether this is sufficient to determine the dynamical degrees of freedom at all points in space. That means the question is, can you evolve in space rather than in time?
Okay.
And in these models, evolution in space is as unitary as evolution in time. That's why we call it dual unitary. And as such, I mean, this dual unitarity basically buys you a lot. I mean, it buys you basically that you can find not all, but many dynamical properties of these models analytically.
Okay, I see.
And to me, this is like really cool because, it reminds me of my kind of learning years of chaos theory, because that's how you teach students to chaos theory. You teach them on some models which are exactly solvable, like cat maps. There is this Arnold cat map, which is the picture of a cat, how it gets transformed under the Hamiltonian chaotic mapping. And one such mapping is so simple that you can solve analytically, yet it is chaotic. And to me, this is like an analogy of quantum cat map for a many-body system. These models are so simple that they can be solved exactly even though they are chaotic. Okay. They can be solved, but solved in a statistical sense, of course. You can compute correlation functions, but not individual trajectories, whatever that means. In quantum many-body systems, trajectory has no meaning, but still. They should be considered as an analogy of classical models which can be solved statistically. So, the key feature of these models is this dual unitarity in both orthogonal directions, in directions of space dynamics and time dynamics. And combining the two unitarities can give you exact solutions.
Okay, I see. Just out of curiosity, do you know who came up with this idea, or how did it started, the dual unitary circuits? Is there someone who created?
Well, that's. As far as I know, at least I hope we didn't reinvented it, but we invented it in 2019, or actually 2018. We came up with the exact solution for what we called, or what I called, Kick-Teasing model.
Okay.
So it's a kind of a transverse or tilted, actually, two-field teasing model, but not in static field, but in periodically pulsing field. Mm. And this model is discrete in space and time. It's a Floquet system. It can be phrased as a quantum circuit. And this is a model I played with 20 years ago when I started when I started my journey in many-body physics. I played with this model numerically, early 2000s or even before. But then we, with Bruno Bertini, who was a postdoc in my group at that time, and Pavel Kos, who just began his PhD, then we got again interested in this, and we found some tricks how to find spectral form factor for this model. These tricks were completely convoluted and abstract, and it was very hard to write a paper. Nobody understood the paper.
I can understand that.
Yeah, but still, the paper was a breakthrough, I think.
Yeah,
but method was so convoluted, and even for us, it was difficult to interpret. And then 6 months later, or maybe less than a year later, we realized what is really the defining feature of this exact solution is this double unitarity. And this allowed us to immediately generalize this to arbitrary circuits with some very simple condition. This is not so fine-tuned property as you might naively think, this dual unitarity. You just have to fine-tune 2 out of 16 parameters for a general circuit, for a general Floquet circuit. If you think of qubits, it's like two states per side, 2 sides, so you have a gate on two adjacent sides, so it's 4 states, 2 qubits, so it's 4 by 4 unitary matrix. It's 16 parameters, 4 square, right?
Okay.
16 real parameters. You have to tune just 2 out of 16 parameters to get unitarity also in the space direction. So it's not such a big thing, right? I mean, it's not so fine, so special.
Okay.
Right. So this was 2019. So there was basically 2 papers which I consider quite important. This PRL in 2018 for Kick-Teasing model and generalization to arbitrary dual unitary circuits in 2019. Another PRL. And I think this was our group. Yeah, I mean basically Bertini, Kos, and myself who were proposing this. And it's still kind of, we are still working on these lines. And I think the key question which is puzzling us now at the moment is how to understand perturbations of these dual unitary circuits. So this system seems to be chaotic. I mean, they are chaotic, we can show that. And again, I'm now kind of using analogy in mathematics of dynamical systems that I know. I mean, there a very important concept was the concept of structural stability. Namely, the question whether your chaotic dynamics is stable under perturbations. Meaning, you have some chaotic system, what happens if you shake it a little bit, if you change the Hamiltonian a little bit? Is dynamics still chaotic or can it get completely different? It happens that you can prove structural stability for a large class of the so-called uniformly hyperbolic dynamical systems, systems for which all trajectories are chaotic, that all pairs of trajectories deviate exponentially. There is a uniform butterfly effect, if you want. These problems are provably structurally stable, meaning that if you change some parameter, the dynamics qualitatively doesn't change much.
Okay.
And what I hope is that these models, these dual unitary models, are structurally stable in that sense. So that if you do perturbations of dual unitary circuits, the convergence of perturbative expansion is typically, they are typically convergent.
Okay, I see.
This is very different from perturbation theory in many-body physics in general, in particular when people expand around integrable or free theories, which is typical, right? You take a free theory and you treat interactions as perturbation. There you have lots of trouble with convergence of perturbation expansion, like divergences in field theory, and all that. So now here we hope that we can change this paradigm and get. If you expand around chaotic models, you get convergent expansions. Yeah.
Okay, I see. And I don't know, what are your expectations in the sense that, well, we know we have heard a lot about quantum computation or experiments that have done that they're currently, well, they're advancing a lot. And the reason that I brought this up is also because you recently wrote a piece for Nature that was a companion piece for an experiment that was done in Google. And I think in Google, I don't know the exact, maybe you will explain it better, but what I find interesting is that apparently they seem to use a lot of your ideas in order to do some experiment that is related to integrability,
yes.
In which I don't know if it's precisely a perturbation, but I know that they altered some well-known system, they altered it in some way, and they had some experimental results that maybe were surprising in some way or very, very important in the sense of integrability. I don't know if you would like to speak a bit about that.
Yes, I mean, there was this recent very interesting paper by the Quantum AI Lab at Google, who implemented integrable quantum circuits, the so-called integrable trotterization of XXZ model. That's basically something that we proposed a couple of years ago, 2018, as a more theoretical concept, but as a quantum circuit is directly implementable on quantum simulators. And the point of that simulation, the point of that paper was that integrability might be considered not so difficult to implement. I mean, because you think of integrability as a very, very, very sensitive effect. You might think of it as very sensitive to imperfections. Now, for them, it's a very good benchmark for a quantum computer, right? If you can do this, if they can implement the gates accurately enough so that they see all the exotic features of integrability, then they should be very happy that they can control things to a large degree.
Okay.
Chaos is more stable, as I told you earlier. I mean, chaos is expected to be stable, so people should not be so excited to be able to simulate random circuits. I mean, this was like this first experiments by Google when they claimed quantum supremacy was like on random circuits.
Okay.
Now they try to fine-tune circuits to get them integrable, and that's much more challenging. So that paper was about simulating an integrable quantum circuit, the way we proposed it. and they found results which basically agree with what people would expect.
Okay, I see. And I don't know, because in the last years, maybe last decades, I mean, there has been an advance in this area of quantum computation. It's a very hot topic, and it's a very interesting topic. A lot of quantum science, a lot of the reason that it gets funding is because of the prospects that it could have in terms of quantum computation technology. What is your perspective about this? I don't know, do you have how optimistic are you about the prospect of quantum computation, about actually building? Because I mean, there has been some progress, but I understand there's also very significant difficulties. So I don't know, how optimistic are you about it, or what are your perspectives in terms of quantum computation?
Well, I have kind of twofold view on this problem, not problem, but this issue that you are raising. I mean, one is very optimistic, the other is not so optimistic. I'm very optimistic, or from the selfish point of view, because I like so much what they can achieve and what they will achieve in a couple of years in terms of quantum simulation, because this will be something very useful for theoretical physicists, because they will be able to simulate our models much better than we could simulate them now in classical supercomputing clusters. Okay. So that is already happening, and it will happen. I mean, now they are already more or less at the level which is hardly simulable by classical supercomputers, but in a couple of years they will go beyond. Okay. So that's super cool for theoretical physics. Now, the other question is, of course, whether it will be useful for someone who actually want to invest money and get profit at the end. That's something that is dangerous, because now we see these new companies coming up, and not new, but they are basically divisions of existing very rich companies like IBM and Google and Honeywell and so on. And these companies are investing huge amounts of money, and it's easy to get, at least it was easy to get investment, in particular during pandemic times, because money was for free. So it was kind of nice show off to invest money and say that you get a quantum computer working. And it's like, I mean, I'm worried that this is like a pyramid scheme, right? Okay, so as long as people invest money, the value of these companies grows. But at some point, someone would say emperor is naked, and then money will go, right? Because still there is no profit. I mean, there is nothing that would benefit some private companies, really. I mean, we still cannot crack I don't know, bank codes, for example, with quantum computers, or they are still not of no really advantage for military, for example, who is also traditionally very interested in these things. Mm-hmm. So, of course, I don't want to say that should be the goal, but what I'm saying is that I don't see clearly the interest of big players. I mean, now the interest was just a flagship, right? Let's show that it works, and our company, Google, will look nice. People will trust Google even more, and they will invest it even more. But I'm worried that this will kind of end at some point, and that we have to provide something more useful for the society. And I'm not seeing this yet now.
Yeah, I guess sometimes it can be hard a bit to convince society or the people that, because I really think like quantum research is important, and it's very nice. It's very interesting that there has been a lot of progress in this area. But sometimes I guess it's difficult to explain to people that maybe sometimes this don't necessarily has a practical application. But that doesn't mean that it's not important. I think there is a very important cultural value to have more understanding about the system. Of course, if there is an important application, that will be very positive. But sometimes people want to be assured that there's going to be something that's going to, improve your life in a very practical way. And I guess it's not always this necessarily the case.
No, and I think the best thing happens when you don't plan any application. So quantum computer, of course, is... I would love to see that quantum computers would be financed by public money. But, as long as they were financed by public money, the progress was slow. Okay. So the progress became much faster when big companies entered the game. But why they entered the game, as I tried to elaborate previously, I'm not sure. So, and I'm not convinced that this will continue. But I prefer, because in spirit, I'm a fundamental scientist, so I don't care about applications. I think applications come as long as things are really cool and interesting from fundamental point of view. Applications come. They always came. We know that, right? From history. So I don't care so much about this, but of course we should care, because the progress depends on how much money we invest into that. So it's kind of not clear.
Okay, I see, I understand.
What's the best attitude? Yeah.
Yes. No, but I do understand your position, and I think. But I just want to emphasize that that is like I really think like the research that has been done in quantum science in the last years, I think it's very important, and like I don't think if we don't build like the perfect quantum computer that can decrypt, I don't think it necessarily will be it will not be like it was lost research or something. I think like the understanding is there, so we actually have gained understanding.
I don't think it was in vain. I mean, nothing was really in vain. I mean, it's really very useful what we have learned so far about implementability of quantum computation. I mean, and I think, I mean, now when we are hearing this, I mean, also in rich countries like Germany are building this Munich Quantum Valley. I mean, this conglomerate of, I think, essentially state-sponsored research institutes. So, I mean, this could be like, I mean, Europe could show to US, okay, that this can be also sponsored by public money. I mean, maybe this could be a kind of because at the end, I don't believe that this can work if it's only sponsored by private money. So there has to be a balance. But in US, it's hard, right? In US, public money will, I mean, private money will take, it's already taken over. So. But in Europe, we have to kind of counterbalance it by.
Okay, I see. But I don't know, I find it curious because, for example, I don't know, the LHC, I mean, that was funded with public money and it was possible. And I mean, now we have it, but I mean, it was also a very ambitious project that it could work. So what I'm trying to say is like, in theory, I guess it should be possible to, with public money, to do advance in terms of.
It should be possible, yeah. But in this particular case, it turned out that with help of private companies, it went much faster.
Okay, I see. Yeah, I understand. And
I'm not sure why it doesn't go faster for problems like fusion. I mean, problem like fusion is much more probably it's much more difficult, but it doesn't matter how much money you pump. It's still decades away, I guess. But
I guess
computer seems to be easier.
I mean, with governments and public money, there's always. At least here, my experience in Europe is that I feel there's too much bureaucracy, and I understand, yes, there can be a bit bureaucracy, it's important, but when it's too much, I feel like sometimes, and especially in the European Union, when you have, but for very ambitious projects, I don't think any country alone can do it, like there has to be a certain level of cooperation, but sometimes to actually have this cooperation and have all these parts to agree on something, it can be very complicated. It's not, I think like it's not really a question of science, it's more a question of social and politics. And
politics.
And in a way that sometimes can be more complicated.
Yeah.
Okay. So maybe one of the last topics that I want to bring is, and I feel like sometimes there's a bit of reluctance from quantum scientists to talk about, is the topic of your work. I don't know if, as far as I understand, it has not deal directly with foundations of quantum mechanics, or will you argue that yes?
No.
Okay, but I'm guessing that you must have your opinions about this subject, or I don't know if you give it a lot of thought or not, or
not really. I mean, a little bit, but not really. I mean, I wouldn't say I'm more like I never considered really to enter this issue of interpretations and foundations of quantum mechanics. I mean, for me, it's the structure of quantum mechanics is as good as it can be. I mean, I'm more like this type of person. Shut up and calculate. Even though you see, I mean, my kind of excitement is on the level of on developing mathematical tools to solve interesting models, to find interesting representative solvable models of different phenomena. It's not so much of understanding really whether this is ultimate quantum mechanics or whether we can improve it as a fundamental theory of nature. If you ask me, my best shot would be that this is okay as it is. I mean, there is nothing better than this. But I think this would not be. I mean,
Okay, I see. But I just find it interesting in the sense that I don't know. There seems to be a reluctance about this topic. For some people, it seems to be very important and fundamental to talk about this. For some people, maybe not as much. And I mean, obviously, you clearly know a lot about quantum mechanics, but still, I guess maybe the problem is that sometimes I feel that people can discuss about this topic for years and years and discuss, but I think as long as there is not any kind of experiment that could disprove any type of view, it will just be, I don't want to say lost talk, but in a way it's hard to see that there's going to be some progress if there's not any type of experiments that you can do to distinguish between all these things, interpretations, quantum mechanics.
Yeah, and I don't think there has been any experiment suggesting anything strange with quantum mechanics the way we know it and the way we interpret it. So I don't think. I mean, I wouldn't. Well, at least I will. I'm not spending my time thinking on this, to be honest.
Okay, I see.
I think, I believe more like in this phenomena of, this principle of emergence, right? So when you have sufficiently complicated system, it organizes in a way that it doesn't matter so much what really the ultimate microscopic theory is. I mean, as long as it's consistent, it will give you emergent phenomena which are universal. It's more like a condensed matter view, right, of doing fundamental physics.
Okay. And yes, maybe. Well, I mean, we talked a bit, but I'm guessing now, as your current or future research, I guess I have the impression you will keep to do research in these dual unitary circuits. I guess that's maybe your most, the topic that you're...
at the moment, I think the most important topic to me is to understand the stability of many-body, dual unitary many-body dynamics. So, chaotic many-body dynamics that we can fully control. And then we would perturb it a little bit and see how much we can, how far we can go. For example, there is this very interesting phenomenon of many-body localization that we have been also participating in. There has been some discussion recently because we have suggested that this phenomenon is not so well understood that people have thought. And I think what I really like is to have some models for which I can really control this putative many-body transition or show that there is really no transition from a rigorous point of view in certain category of models. But I think the way I would approach, and I plan to approach this problem, is to start from an ergodic side, not localized side. I mean, what people do usually is to start from a localized side, like an Anderson problem, which is localized, and then they switch on interactions. And then they argue that for sufficiently strong disorder, interactions don't destabilize localization.
Okay.
Well, and of course, I don't want to enter this debate here, but there is lots of criticism of this point of view. But I think what is much safer is to start from the opposite side, from the ergodic side, and then switch on disorder. So to start from a strongly chaotic interacting system for which you can fully control dynamics, you can show it's chaotic, and then you perturb it by disorder, and then you can show that at least for sufficient amount of disorder, there is no way of localizing the system.
Okay.
And then maybe we can show there is no way to localize the system full stop.
Okay,
from the methods that we are developing. But that's something that I'm looking forward to in next years, maybe.
Okay, so good, very good. Maybe lastly, we also, the point that I was trying to, the reason that I want to do this is because I want to kind of connect the research of a scientist with society in a way, and I think sometimes, there are people know the scientists like, I don't know, Neil deGrasse Tyson and Bill Nye, which I know that their work is to do divulgation of science, but I think it's also important to sometimes to hear actual scientists who do like research. I don't want to dismiss the work of the divulgators of science, it's very important, but I also think it's important to hear directly from scientists what they do in a way, so people can have a better idea of what research takes place. And and also maybe a bit, so people can know better science and stuff. From the social perspective, when you don't do science, is there any hobby or something that interests you? Or I know that you're a very busy person and science takes a lot of your time, but I don't know, when you have free time, something that...
Well, it's... it's true, probably science takes most of my time.
Okay, I see.
I like to be physically active to some extent, so I'm not doing any heavy sports, but I like to be active at least a couple of times a week, do some hiking or skiing if possible. Now it's a very poor winter, but I'm quite passionate skier. I like to listen to music, watch some nice movie and this type of thing. So this is more like a relaxing activity. Sometimes to read a nice book, fiction book, things like that. But I don't really have other hobbies.
No, but that's so good. Good reading, movies, that's good. Okay, that's good. So I think that's it. But thank you very much for accepting. And it was very nice talking to you. Thank you very much.
Thank you, Guillermo.
Okay,
thanks.
Okay, it should be okay.
Okay.